Okay, so we're doing a little conversation about Huckle theory, kind of continuing what we were talking about last night with the butadiene, to talk about simplifications, right? And so last night when we were looking at this, we were like, okay, we've got 30 plus electrons. We could do this as a 30 by 30, or we can do some simplifications. I lost my pen cap and I'm getting ink all over my hands. Where did my pen cap go? Awkward. You can do it as a 30 by 30. That's excessive. You could treat the core electrons as one like electron group, and that's another thing you can do to simplify things. You can do valence bond theory and split this into like 12 different diatomic problems. And we're like, but since this is a conjugated system, you can also use Huckle theory. And essentially what Huckle theory is going to do is we're going to have 4 carbon centers. And we're just going to treat 4 p electrons. That are delocalized. So we're really just going to focus on the electrons that are in the unhybridized p orbitals, these electrons that kind of have some mobility to them. And the thing that's fun, cool, interesting about Huckle theory is if you do the full like 30 by 30 treatment, you actually get a really similar result. So Huckle theory is this really same thing. If you did the 12 diatomic problems, the valence bond theory, you get a really similar result. So you can actually get a really reasonable result with just doing a 4 by 4. And the thing that I didn't write down in class yesterday because I was kind of rushing through is you end up with your H11 minus your ES11 and your H12 minus your ES12 and your H13 minus your ES13 and your H14 minus your ES14, and then you fill it all in, right? You make a 4 by 4 matrix. We've only done this as a 2 by 2 by so far. Then you've got your H21 minus your ES21 and your H22 minus your ES22, so on and so forth. And what Huckle theory essentially says is like, look, if I'm looking at one electron on this one carbon, or one electron on this one carbon, or one electron, essentially all my H11s and all my H11s are going to simplify down to one value, and all my S11s are going to simplify down to one value. And that's what I showed in that matrix that I just put up real quick. It was like diagonals all the same, off diagonal elements, we'll deal with it, right? So what the textbook does is it refers to H11 as just some term alpha, which I don't like that much because we already have alpha for spin. So I'm just going to leave them all labeled as H11. And they're all going to be like some value associated with them. The S11s, it turns out, are all normalized, so those all go to 1. And then the H21 minus ES21 is equal to some other value. And again, in the textbook, they call that beta. And I want to come up with a different label than beta for it. Actually, let's just stick with alpha and beta because that's how the assignment sets it up. That's how the textbook sets it up. But I'm going to add some labels so we don't confuse it with spin. I'm going to call it alpha 11. I'm going to call it beta 21. Right, and the subscript is just so we're like, that's definitely not spin, because it's not like parenthesis thing. It's just it's an integral that we're representing. And what we can actually say, the part that kind of becomes interesting, is we say, okay, so that's H21, and this term essentially says, if I've got an electron over here, how much is it interacting with that other nucleus? Right, that's what our off-diagonal elements have told us when we were looking at H2. Our off-diagonal element was that exchange integral. What's that mobility of the electron between two nuclei? So this term would be essentially saying something along the lines of how likely is this electron to drift over to the other nucleus? And so we have some value associated with that.
How did you pick pick that electron for that equation as opposed to like a different one?
We could have picked it. It turns out, like, I could have picked like this one electron doing it, right? We could have picked any. I did a 2-1, right? So I just picked, if I label these carbons as like carbon 1, carbon 2, carbon 3, carbon 4, I'm doing like the 1, 2 or the 2, 1. And it turns out the 1, 2 and the 2, 1, same value. So I can go ahead and say that as well. H12 minus ES12 is also going to be equal to beta 2,1. Right? Those two things end up being the same because it's the electron jumping between the two nuclei. The other thing that we can ask, and it turns out that for any neighbors, so for like 1 to 2, we get that same beta value. For 2 to 3, we get that same beta value. For 3 to 4, we get that same beta value. So, the integrals are the same value. So I can start simplifying this integral, if I may. Yeah? Okay. So we can start simplifying the integral. And again, the textbook does a really wonderful walkthrough of this, where my 4 terms I'm going to have 1, 2, 3, 4 alpha 1, 1s down the diagonal. I'm going to have a beta 1, 2 and a beta 1, 2 between those two. And it's going to be the same integrals if it's 1, 2 or 2, 3. So I'm just going to keep it as a beta 1, 2 and a beta 1, 2. Right? So my nearest neighbor always has that effect going on. And the same thing if I do 3, 4, 4, 3, it's the same integrals, beta 1, 2, beta 1, 2. Zeros for now everywhere else. Right? And so what those zeros tell us is like, hey, the ability of that electron to drift all the way from 1 over to 3 is approximately 0. Now in your coding assignment, it's like, oh ho ho, it's not actually 0. There's actually some other term for the H13 minus S13. Right, there's going to be some beta for that electron going from the carbon 1 over to carbon 3. Typically, it's going to be a much smaller energy. Right, the alpha terms are usually pretty large. The beta terms are a small correction to those alpha terms. And then if we had these second beta terms, these beta 1, 3 terms, those end up being a small correction onto the correction. So last night I plugged in some generic numbers to work on this and do the diagonalization and show how we get the different phases. I didn't get to send the pictures. I meant to send the pictures. I'm going to make a note to self, right, of what those different wave functions look like. We just said they end up being symmetric or not symmetric. And across this, right, do you remember the solutions from last night? Me either. Let's get them real quick. So I'm going to pull up my MATLAB code. And I'm going to rerun it. It should be the last thing I ran, so it should be the first thing we see. But essentially what we can think of is we can think of this as a chain of p orbitals on the first carbon, the second carbon, the third carbon, and the fourth carbon. And we can say, are those things the same size? Are they the same phase? What's going on? Again, saying that we're only dealing with the nearest neighbor overlap. What happens?
Would the alpha have energy also, like minus E?
Yeah. Like the minus E's on there? Yeah, we can leave that out because the reason I can leave that out in my setup is because the process of diagonalization, taking the determinant, will bring the minus E back in. So like when it's like a matrix like this, yes, there should be minus E's along the diagonal. You're correct.
So for MATLAB, we shouldn't plug in the E.
You don't have to.
Okay.
Right, and that's why you're getting that weird like E equation.
Yeah.
So MATLAB is essentially saying, here's a weird E equation that you have to solve that's a sixth order equation, and you're going to get six possible answers to it.
Okay, I ended up solving for that, and it gave me like plus or minus values, and is that what I use to calculate the energy?
Yeah. Yeah. That's precisely it. Okay, so let me run this code real quick. Nope, that's not the right code. Where'd my code go? Oh, there it is. Okay. So I run my code. Okay, so my symmetric case is all the same phase, 0.37, 0.6, 0.37. So my orbitals are not actually evenly contributing. The two middle orbitals are about twice as big as my end orbitals. Pretend I can draw, please. All the same phase are, the vector we solve for is 0.371, 0.601, 0.601, and 0.371. That's one of our possibilities, right? That's our C1, C2, C3, C4. And so I tried to draw the size of those p orbitals to communicate bigger and smaller, because the middle two are not quite double, 2/3 as big, right? 3.7 versus 0.6. And that's like, this would be, that would be one of my possible 5 functions. Another one of my possible 5 functions, should I do the second one or the last one? There's 3 other to pick from. Which one do you want to see? Let's do the second one. Okay. The second one is 0.6, 0.3, 0.3, 0.6. So the second one ends up being, again, 4 p orbitals, big on the ends, smaller in the middle, big on the end, but the phase flips halfway through. This one is a 0.601. This is a 0.371. This one is a negative 0.371. And this one is a positive, negative 0.601. So I get this flip in the addition and the subtraction. And the way we think about this is we say, look, there's essentially some constructive interference over here and constructive interference over here, but we end up with this node in between where there's a flip through 0. And so we can start to understand how the bonding across the molecule behaves when we're in lower energy states versus higher energy states. And we can continue to analyze all of those. And that's kind of what we get from doing the diagonalization. We get the energies, so we know which one is lowest and which one is highest. And we get this list of coefficients to know what the orbitals look like. Now, let's talk a little bit more. So that's kind of where we're leading. But let's talk about some ways where we can simplify. And again, textbook does a great walkthrough of this. But let's talk about ways we can simplify this alpha-beta matrix thing. Shall we? Okay. I'm going to erase a lot of the stuff around that alpha-beta. I'm going to ask you to remember these definitions of the alphas and betas are just defining terms. And we could add some extra terms here. If we knew there was some interactions there, we could do that. But let's simplify this a little bit first. And there's kind of 2 steps to simplifying it. And depending on where you look this up, there's some really nice places where they do this. I meant to send out the Chem353 link because they have some really nice images, particularly for cyclobutadiene, where they show these phase pictures really better than I can draw them. But they simplify in a different way than your textbook does. So I'm going to do it the way that the textbook does, and then I'll explain the way they do it as well. So the first thing you can do is you can split this, instead of having it as one matrix, we can do it as if two matrices are added together. So you can have a matrix that's alpha, 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 alpha. Right, and when we get used to dealing with matrices, oh, I missed a 0. I missed a lot of zeros. Hold on, let me write that a little bit cleaner. Alpha 1, 1, 0, 2, 3. Alpha 1, 1, 1, 2. 0, 0. Alpha 2, 2. Alpha 1, 1, 0. Alpha 1, 1. And then we just add it and to this one. Right, so if I add these two things back together, the middle becomes alphas, I get the same thing back. And then they do an extra step of simplification. They say, okay, in this one, you just factor out the alpha 1, 1 from everything, and you just get 1s along the diagonal. It's already a diagonal matrix. That part's already diagonalized. We don't have to do anything to that. That essentially defines the average energy that this thing is going to adjust. Right, so this thing defines that middle energy, and then this thing is going to be some variation of that middle energy, up and down. And this thing, you'll notice, like, since all the betas are the same, we can also do a simplification here, where if I gave myself a little bit more space, we can just factor out the beta 1, 2 from the entire matrix, replace all those beta 1, 2s with 1s. Right, and this is nice, because what happens here is I think this came up last night, I think it was during class, where the coefficients for diagonalization are the same regardless of what beta 1, 2 is. I think we saw this for a simpler example when we were doing our hydrogen one, right? I could change those energy values to kind of anything, and that would change the eigenvalues I get, but my coefficients, my C1, my C2, my C3, C4, they were always the same. Because of this symmetry of this matrix that's not diagonal, the process of diagonalizing it always gives the same coefficients. So for this butadiene, the problem that you're doing for your coding assignment, you could pick any values for alpha, beta, and beta, and that will change your eventual energies, but the coefficients for the functions that come out, those will be the same regardless of those different things. Because we set up this matrix by insisting on some geometry of the problem, some interactions of the problem. And that's where the simplifications come in for solving the problems. We say, hey, we know that this has like this set single bond network. We know those are localized electrons. Hey. And so we know they're not moving. That's what allows me to set up this thing being so symmetric. And then we really don't need to worry about the alpha part. In the textbook, they write the alpha part. This 1s along the diagonal is referred to as the identity matrix. And we can just write that down. Is a squiggle above for matrix? What's the notation for something being a matrix? Does that mean it's a matrix? It's been a while since I've used that notation. So this is the identity matrix. It's gonna bother me. It bothered me last night too, so I want to look. ones underneath. Boldface. Oh, it's just, they usually just make it bold. But I have trouble drawing bold on a board. And so the other option that people use is a tilde underneath. That's not what I remember. Okay. So if you ever see a letter in bold, it's meaning matrix, or they put like a tilde underneath it. Since I have trouble drawing bold on the whiteboard, I'm going to go with what I just found, and I'm going to put, I remember it being a tilde above. So I'm going to go with what I just found, and you're going to put the tilde below. That it's the identity matrix. So the I matrix is just ones along the diagonals. It's a 4 by 4. And then I've got this non-diagonal matrix. I diagonalize that using MATLAB. So it turns out, and the problem I did last night, I had 100s here and 50s here. Like I had my 50s along the off diagonal. So I could have just diagonalized this. I'm going to get some values associated with that. Those values times 50 plus 100 would have given me the same answers that I got with all of those numbers in. So there's that kind of like difference of how we deal with it. Let's look at the particular 4 solutions. There's several different ways to simplify this. The way that, and I'm going to send this link out right after this, but the way that Chem353 does it is it divides everything by beta, so you get ones along here, and then you get this alpha over beta term along the diagonal, and then it splits the alpha over beta term over. So it just essentially divides this by beta. And it says like you're going to have your alpha 1, 1 divided by beta 1, 2. And now you really just have to diagonalize that thing. And that thing is going to give you the eigenvalues. You need to add those eigenvalues to these things. But it's this further simplification that really makes it obvious you just have to diagonalize this thing in terms of ones. And you don't need all of the information in there. And so there's other different ways to kind of simplify it. But no matter how we simplify it, for the way that I have this set up, that's always the matrix that we're going to be diagonalizing. Now, what kind of other quirks can we do to this? First quirk is we could add these small extra terms. I could add in this 1, 3 term. I'm going to do it in a different color so it looks a little more obvious. Right? We can add in this extra there's this beta 1, 3 term so that this first carbon and this third carbon do actually have some connection. Right? And then the second carbon and the fourth carbon would also have some connections. So that would be 2, 4, and 4, 2 would have some connection. And so I'd end up with those 2 extra things in there. And I'm putting them as like a tenth as big. And we usually see that like the first interaction is larger than the second interaction. You could probably even add in, if you wanted to, add in some 1, 4 connection. That would be like 0.01. And now we just diagonalize this matrix. And we're going to get a different list of eigenvalues. We're going to get a different list of 4 coefficient vectors for our different possible wave functions, and we can draw different pictures for those. And we'll look at some particular pictures. So that's another thing we could do to modify it. Another thing we could do to modify it would be to change the entire function, like to change the chemical. So let's say I wanted to have carbon 1 and carbon 4 really connected to each other, like had a strong interaction. That would no longer be butadiene. That would be cyclobutadiene. And in that situation, if I go back to forget my 1,3 interaction, in this situation, carbon 1 and carbon 4 are as connected as carbon 1 and carbon 2. So I end up with these corner values having 1s. And obviously, I'm going to end up with different solutions in that situation, different wave functions, so different lists of coefficients and different energy values associated with it. And this gets closer to what you have in your assignment, because you have a cyclic, you have is it benzene? right? You have a cyclic molecule where carbon 1 and carbon 6 are actually connected to each other. And yeah, and then around the ring, right? And so you just end up with a matrix like this to diagonalize, and the different relationships to the energies. But let's go back. Can I rewind a little bit back to the wave functions for cyclobutadiene? Sorry, for just butadiene, not cyclo. So if we look back at butadiene, we got this matrix to diagonalize. We don't really have to do any of the simplifications to diagonalize it. We can do it this complicated and have MATLAB do it for us. A lot of the simplifications make it so it's easier. Like right now, if I wanted to modify this code, I'd have to go in. I could probably just do one line of code that says beta equals at the beginning, or like b equals, and I could just be like, do it for 1, do it for 2, and like see how changing that overlap, that interaction energy affects my functions. So there's some simplifications from writing it as just like a series of ones. But let's look at the 4 answers that we get out from the code we did last night. So I got 4 different energies. I'm going to do it for my hundreds and 50s. And so I got 4 different energies. That's hard to see. Oh, that didn't help. I'm going to do a little bit of rounding. 180.9 E2 is equal to negative 130.9. E3, I didn't give myself enough space. E4. I'm not going to, I'll write down E4, but I didn't really give myself enough space for that. Negative 69.1. And then E4 is negative 19.1. So lowest energy to highest energy, I probably should have written in a flipped way, but this is the way it spit out. MATLAB always spits out your answers from like the smallest number to the largest number. Since these are negatives, that's going to be our lowest energy to our highest energy. And the reason I want to list it opposite is because whenever I write things on the board, I usually write my lowest energies lowest. So it's like, should have thought of that beforehand. And then we've got this diagonalizing matrix. We already looked at the first answer. Right, where I'm using the size of the orbitals to communicate the coefficients. I'm going to simplify those. For our first answer, we got 0.3, 0.6, 0.6, 0.3, 37, 61, 61, 601. Just leave it as 60. Just leave it as 0.6. Right, so I drew these a little bit bigger to communicate that larger contribution, and they're all in the same phase. And then we've got our second energy. I'm going to draw that one to the side over here. And this one was big, small, small, big. Yeah. There's a bigger one, 2 smaller ones in the middle, and a bigger one on the end. And the phasing flipped. And it was 0.6, 0.37, negative 0.37, 0.6. So that gives us some visualization of what's going on. And then the reason I'm stopping there right now is because we only have 4 p electrons. So I can fit 2 electrons in this one, and I can fit 2 electrons in that one. And it's going to fit all of my electrons. If I wanted to know the total energy, 2 times that plus 2 times that, total energy. If I wanted to know what's my next highest, what's the gap between my 2 energy levels, I would just look at the change in energy between those 2. That gives you that gap in energy.
Would it be 2 times that minus that? 2 times the top minus the, yeah.
No, we
Or
would
is it
just, because we just get the gap between the levels, not the occupation. So if I wrote this out, the way that this looks is I have like a negative 180, a negative 130, and then a pretty big jump up to negative 69, and then negative 19. And so the only thing that I'm looking for is the gap here, that delta E of how, essentially what I'm looking for is what wavelength would it take to promote an electron. So I just look for the delta E. Off by 50, off by 50, off by, what's 30? Off by 60?
Mm.
So yeah, it's like gap of 50, gap of 60, gap of 50. And it turns out these two are bonding orbitals, and these two are going to be anti-bonding orbitals, because it's mostly in phase. Still a lot in phase, just one node. If I left enough space to draw, let me see, I'm going to squeeze E3 in here, just because I haven't drawn that one yet, and I kind of want to see what it looks like.
I have a quick question.
Yeah.
So we chose that delta E because it's the homolumo, or
Yeah,
it's the biggest gap?
Homolumo.
Okay.
We only have 4, in the example I'm doing, we only have 4 p electrons, so I occupy my levels 2 electrons per level.
Yeah.
2 p electrons per p level.
Okay, perfect.
Of course, we know there's a lot more electrons in this molecule. The whole point of Huckle theory is to say, look, we don't need to do a lot of that. A lot of that is an over-parameterization. As long as we have some restrictions where we can generate these Huckle matrices. This one is third one, 6336. So this one goes big, small, small, big, kind of like the other one, except for this one goes negative across the middle. And so where we have our phase flips is we end up with, ooh, that purple looks black. We end up with 2 places where we have phase flips instead of just one. I'm going to do that in green. Right, I've got a phase flip there, phase flip there, phase flip there. So I've got these nodes of no electron density. And the place where I do have some overlapping in the middle, it's a smaller contribution than the big parts. So this one, even though it does have some bonding characteristics, it's mostly anti-bonding. And if I do the last one, it's just every single one, it flips every time, and you end up always having, like, you have nodes between every carbon. And that's what I would have done if I had 10 more minutes last night. Questions? Did that clear up a lot of your questions?
Yeah, I think so. I guess like now my question is whether I'm using my calculation correctly.
We can take a look. Let me get some other, make sure there aren't any other questions about this, then I'll stop the recording and we can do like detailed questions. Did that clear up your questions? Other questions?
What about this?
Okay, cool. What other questions do you have?
I had a question about the midterm, but if you were doing coding stuff like related to this, like.
Yeah, let's look at that. I'm going to go
Yeah.
ahead and pause the recording.